SwayamPrabha. Digital India. Educated India.
In the last class, we have discussed the motion quantities of a rigid body when it moves about a point. We have found that the inertial properties of a rigid body is a far more complex quantity and which can be represented by 6 independent quantities, and we term it as a tensor and we gave the name as inertia tensor. So if this be the rigid body under consideration, its translational motion can be considered to be a particle motion type of motion, where the whole mass of the rigid body may be considered to be concentrated at the center of mass, and the angular motion about the center of mass or any other fixed point O can be represented by an instantaneous angular rotation about an instantaneous axis which changes its position both relative to space and time. And if the angular velocity at a particular instant be omega vector, then we can resolve it into various components along 3 mutually perpendicular directions, x, y, z, as omega x, omega y and omega z. So these are the components of the angular velocity of the rigid body along these 3 directions, small x, small y, small z. We should also remember that there is another set of coordinate, capital X, capital Y, capital Z, and without losing much generality in the results, we can make the 2 origins coincide at O. This smaller XYZ system has an instantaneous or an angular velocity omega with respect to the fixed frame of reference. Now we have to remember that the angular velocity of this frame XYZ omega is different from the angular velocity of the rigid body, which is omega. So this is the situation. We have a fixed frame of reference capital XYZ, we have a moving frame of reference small xyz moving with an angular velocity capital omega, and the rigid body which is rotating with an instantaneous angular velocity omega. So we have, so the angular momentum vector L can be expressed as in the form of 3 components Lx, Ly and Lz. And we have seen that the expression for each Lx, Ly, Lz can be expressed as Ixx omega x minus Ixy omega y minus Ixz omega z. We can express this as minus Iyx omega x plus I y y omega y minus I y z omega z, and this component as minus I zx omega x minus I yz zy omega y plus I z omega z, where Ixx is the second mass moment of inertia, or simply the moment of inertia of the rigid body about the x-axis. So this rigid body now along this direction x, along this direction y, and along this direction z, if I measure or define its moment of inertia about x-axis, that is Ixx. The moment of inertia about a rotation, about an axis y is Iyy, and moment of inertia for the rotation about axis z is Izz. So these were familiar terms. We have seen the concept of moment of inertia even in plane motion of rigid bodies in our dynamical courses. However, these quantities Ixy, Ixz, Iyz, they are something new which you have not encountered before, and they are called the product of inertia. Now we have also seen that this complex situation can be made much simpler if we select these small x, small y and small z directions in a way so that the product of inertia vanishes. And when these directions x, y, z, when they are along the principal axis of the rigid body, then Ixy is equal to Iyx equal to Iyz equal to Izy equal to Izx equal to Ixz equal to 0. So all the products of inertia vanish. So therefore, the components of angular momentum of the rigid body Lx, Ly, Lz can be represented very simply in this form. So if this rigid body is having an instantaneous angular velocity of omega, its angular momentum L will be something like this. In planar motion it doesn't happen. So there we have seen the angular velocity vector and the angular momentum vector generally coincide. But in this case they are not coinciding, except for the situation where all the moments of inertia are, principal moments of inertia are same. Then only Lx, Ly, Lz components will be proportional to omega x, omega y, omega z, which means that both the vectors will be along the same direction. But in general it doesn't happen so. So therefore now onwards we will always try to express our quantities and equations through the use of this principal axis, or through the use of this condition when the products of inertia vanish. Now determination of this principal axis is a very important exercise in dynamics, and there is a general procedure with the help of which, when we know for a particular xyz system all these quantities Ixx, Iyy, Izz and the products of inertia, there is a method of determining the principal axis for which the products of inertia will vanish. Now in most of the cases in engineering applications you will find we have a somewhat happier situation, because we don't generally deal with bodies of very general shape. In most engineering applications objects will have certain symmetry, like say for example a roller or a disc things like this, a gear, clutch plate, all such things, or simple rod-like objects. In most cases, these are the kinds of component shapes we will be dealing with. And for such cases, it is easy to determine the principal axis by observation. If the body is symmetric, then all axes of symmetry will be principal axis. So in the case of that roller, for example, one axis of symmetry is very obviously this one. So this will be one principal axis. Then any two mutually perpendicular lines any other two mutually perpendicular lines will be principal axis. Similarly, if the body is not an axisymmetric body like this, but say a rectangular object like this, with no circular or rotational symmetry, then principal axis will be obviously this is one axis of symmetry, this is one axis of symmetry, and this is the other axis of symmetry. They all meet at the center of the body. So here again we can use x, y, z as principal axis. The difference between this and this is that here only y direction is fixed. X and z can be any two mutually perpendicular directions where both x and z are at right angles to y. In this case that is not so. There the directions of x, y, z are all uniquely determined. Similarly, you will find that in this case again it's an axisymmetric body, so this will be one principal axis, and then any two mutually perpendicular line because of this circular symmetry can be principal axis. In case of a rod-like objects, again this is one axis of symmetry, and this, if it is a line, then any two mutually perpendicular direction or lines can be chosen as principal axis. So except in rare situations where the bodies don't have degree of symmetry, we can find out the principal axis by observation. In these cases again there are two types of objects. In one case the bodies are axisymmetric where only one principal axis is fixed, the other two can be chosen, and the moment of inertia they do not change when we vary this x and z along this direction. Same is the case here, but here the body, it has three unique directions which can be taken as principal axis. Now when we consider a body under external forces and moments, we can find out what will be the subsequent motion of that rigid body. That is what we want to do next. So we know a very simple case is a particle of mass m when subjected to a force F will produce an acceleration in this direction. That is simple Newton's law, and the relationship between these three quantities is very well known to all of us, is this. Now instead of a particle, if you take a rigid body, you have already seen in our first module lectures that if the resultant force, that means the resultant of all the external forces acting on the body, can be represented by a force F, then the linear acceleration of this center of mass will be A, which will be again mass of the body. So till this case is very similar. In translational motion, the rigid body behaves like a particle, as if the whole mass has been concentrated at the center of mass, where the resultant of all the external forces are acting, and the acceleration of the center mass will be this. The real difficult task or complicated task will be to find out the angular acceleration of a body when it is subjected to external moment and the body has its own angular velocity at a particular instant. So that is what now we will do. Now if the three components of the externally applied moments acting on a rigid body about its center of mass, then this mx, my, mz are the components of this, then we can show that this will be nothing but rate of change of the angular momentum x component. This is nothing but rate of change of angular momentum y component and rate of change of angular momentum z component. Because we can easily prove that m is equal to L vector dot. Proving this is not very difficult. If we treat this rigid body as a system of particles where the distance between any two particles remains constant, as the definition of rigid body says, then we can always derive this relation. So this is the center of mass. Say the particle, ith particle with a mass dm, the external force which is acting on this ith particle is Fi, and this particle is subjected to, apart from this external force, it is subjected to interactive force with other particles. So if we take a jth particle, then this will be subjected to a force which we call, say, Pij. It means that it is the force on this ith particle due to the jth particle. So here, to get the total force on this ith particle, we have to sum it up for all the other particles of the rigid body, that is j goes from 1 to all except I, because one particle cannot exert force on itself. So therefore, you will find that if the position vector of this be rho I, then the moment, or rather the total force first of all, is how much? Is Fi plus Pij, j from 1 to n, except and j is not equal to I. So that is the total force acting on the particle, and this will produce, this will be nothing but, if this is a fixed point, we can show that this will be nothing but This is the mass and this is the acceleration of the particle, treating the center of mass as a fixed point. If it is not a fixed point, then also we can show that the same kind of formulation will be valid. That can be shown later. So therefore, if we want to now find out what is the moment of all these forces about point G, it will be what? What is the moment due to this total force acting here? This will be rho I cross Now this, of course, remember, since we are finding the total, we have to sum it up for all particles. So here you will find that this is going to be rho I cross Fi sound over I plus. Now when we do this, we find that it is going to be a double sum I and j of rho I cross Pij. Now this is an interesting thing, because Pij is a force this, and because of Newton's third law, the equal and opposite force Pji will be just equal and opposite. So when you vary this the index for all the particles, you will find for each Pij there will be one negative Pji which will oppose the effect of this. So therefore the resultant of this will be equal to 0, and this is equal to and this is nothing but the moment of the external forces. Here it was the total, but actually we have seen that the internal forces cannot produce any general moment. So this is the equivalent of Newton's law for a rigid body in rotary motion. Now this quantity can be shown as the L dot. So to do that, I think you have to only express rho into its components x, y, z. Let me see. So to show this, what we start with is that rho I dot is the velocity of the particle. When multiplied by dmi, we get the linear momentum of the particle. So rho I cross the linear momentum is by definition the angular momentum. Now if we sum it up for all the particles, we get the angular momentum vector for the rigid body. So this is the expression for angular momentum of the rigid body about point G, from where rho I is being measured. Now if I differentiate Li with respect to time, what we will get? We will get rho I dot cross rho I dot dmi plus rho I cross rho I2 dot dmi, and summed over all particles. But we all know that the cross product of the same identical vectors will be 0. So this term becomes 0 and only this remains. So we find that this is nothing but rate of change of angular momentum, which is equal to, again we have shown, nothing but the resultant moment of the external forces or resultant externally applied moment. So therefore the equivalent to Newton's law, that moment applied is equal to rate of change of angular momentum. So therefore now we have to express this in the kind of quantities which you have been using. Here it is just a very general form. So what we do here, we represent the angular momentum in terms of the angular velocity components and the inertial property of the rigid body. So therefore Lx, Ly, Lz we have already seen. Lx is equal to I xx omega x minus, this one, Ly is equal to I y y omega y, Lz equal to I z z omega z. Now all the time you have to keep in mind is that small xyz system is rigidly attached to the rigid body under consideration. So therefore, so far as the small xyz axis that observer is concerned, no change in Ixx, Iyy, Izz can be seen. Or in other words, Ixx, Iyy, Izz do not change with time as seen from small xyz system. So L is equal to I omega vector. Now we have seen that rate of change of angular momentum, we have to all the time remember that this rate of change is with respect to the absolute frame or capital XY. So here it will be plus, since XYZ system is rigidly attached, that frame's angular velocity is also omega, and this is the. Now here, if we want to now find out what will be dl dt. Now L we have seen is the components are like this, so we can write it at least one more, I Lx j Ly plus k Lz dt xyz plus omega cross L. This now split up into these three components. Now I is a unit vector along the small x direction. So therefore with respect to small xyz system, that vector I does not have any change. So d I hat dt will be 0. So it will be I hat dlx dt in xyz system plus similarly j hat, that unit vector also in xyz system is fixed, so it will not have any change. So when you differentiate this, you will get Now dLx dt, Lx magnitude, now we are talking about the magnitude of Lx, which is given by this. So if we differentiate this with respect to time in the xyz, small xyz frame, then this is a constant quantity in the small xyz system, only this can change. So what we will get, this L dot rate of change of the angular momentum with respect to an absolute frame of reference is equal to I hat I xx. When I differentiate this, only this can change, so it will be omega x dot, that is magnitude of the angular velocity component, plus j I y omega y dot plus k I z omega z dot plus omega cross L. Now omega cross L will be what? We can write it like this: I hat omega x plus j hat omega y plus k hat omega z cross I hat Lx plus j hat Ly plus k hat Lz. So when you do this cross multiplication here, this cross product, then I cross I is 0, I cross j is k omega x Ly, I cross k is minus j omega x Lz, j cross I is minus k omega y Lx, and so this is the complete result. We can next combine terms under I, under j and under k. So rather than writing a long expression, now we can also find out the components of this. Now remember now that this L, rate of change of angular momentum, is nothing but the externally applied moment. So mx will be the x component of this. That means the terms, if you take I hat as common, the term with which I is associated, and that will be I xx omega x dot plus I omega y Lz. Now Lz is nothing but I zz omega z, and the other term is this minus omega z, I Ly is I y omega y. So we have to keep in mind from the very beginning that the small xyz coordinate systems have been chosen in such a way that they are principal axis. Similarly, my will be the j part, that is I y omega y dot then this term was I cross k is minus j, k cross I is j. So therefore this plus omega z, Lx is I xx omega x, and this is omega x Lz, which is I zz omega z, and mz will be the k part, that is I zz omega z dot plus omega x I y omega y, this term, minus this term So in a form when we can remember this, generally it is written like this: Ixx omega x dot. Here we can put this I minus I y omega z plus I z omega y. My is I y omega y dot minus I z omega x plus I x omega z. This form it is easy to remember because x, y, z, it is in circular form, x, y, z, y, z, x, z, x, y. So that's how one can easily remember. And for the situation where the small x, y, z system is rigidly attached to the body, that means its angular velocity and the body's angular velocity are same, then obviously this can be taken common. Minus I y I z omega y omega z. So this is the set of equations where the components of the externally applied resultant moment on the body and its kinematic quantities and the inertial properties are related. This set of equations are sometimes called Euler's equations, as it was first derived by Euler. And this is the form of equation, though it is not perfectly general. Perfectly general form will be that where the small xyz system is not rigidly attached to the body. We will do some such examples in the next lecture if we get time. But this will be the governing equations for all the rigid body motions in 3 dimension we will be doing and we will be applying to machines. So in the next lecture what we intend to do is to solve problems and see that what motions are produced by certain externally applied moments, but more interestingly what we will see that certain motions in machines and its parts, components, produce some moments or some reactions which otherwise we don't find. So we will find some counterintuitive phenomena to take place when we consider the 3-dimensional motion of a rigid body.